In the last to last module, we had learned the various factors upon which the potential energy of any object depends. So they were mass, the gravitational acceleration or the acceleration by which falling objects accelerate, and the height at which the object is placed. Now in this video, let us use a mathematical approach and arrive at the same expression that we had arrived at in the last module. So in the previous video, we had learned that the potential energy of an object is the work that we do on that object. So let us start by first of all drawing my ground here. So this is the ground level, and let's say I have some ball placed at this position. It's at the ground level, and right now it has no kinetic energy. So if I have a ball there, it has no kinetic energy and it has no potential energy because it has no height, so it cannot do any work if I leave it at that height. But now let's say I do some positive work on this ball. So positive work, as discussed in the last video, is giving it some energy. So I'm doing some positive work or giving it some energy, and if I give it, let's say, some work, I do some work on it, some positive work, I give that amount of energy to this, and if I use the work to lift it, I'm actually giving it potential energy, right? I'm not increasing its velocity by increasing its height. I'm not increasing its velocity, and so I'm not giving it kinetic energy, but I'm giving it some potential energy or some energy that is being stored inside this object, and once I leave it, that potential energy gets converted into kinetic energy. So let us first of all, let's say I raise it to some height. Let's say I bring it here from this height. So I raise it by this height, and I'll just remove it from here. So I have raised it by a height h, and let's say the mass of this ball was m, just to be general, and again let's just call the gravitational acceleration g, as we did in the last video. Now we have the various variables here. So now first of all, let us find the work done on this object to take it from this height, so 0 height, to some height h. So we know that the work done on this thing, so obviously we have to do some positive work. Why do we have to do some positive work on the ball? Because we have to give it some energy, right? We have to give it some energy, to be precise, some potential energy. And because if we are giving, let's say, if we are doing 5 joules of positive work, we are in a way giving 5 joules of energy in the form of potential energy, and so its potential energy, PE, should be 5 joules, right? So work done on the ball is equal to its potential energy, or to be precise, the potential energy it gains. But obviously right now it had 0 potential energy, so the potential energy it gains is its potential energy itself. So now we can use this equation to find its potential energy. So let me write the potential energy on this side. So PE equals work done. So we have this expression. Now what is work done? Well, we know that the work done on any object is the force we apply on the object times the distance that the object travels as a result of the application of that force. So PE equals force applied multiplied by distance that the object travels. So in this case, what is the force that we apply? Well, to lift it, we have to, what is the minimum force that we need to apply? Well, so we have to obviously overcome the force of gravity, right? So if we have to lift it, so remember Newton's second law. So Newton's second law says that only an external unbalanced force causes motion. So we have to get some unbalanced force. So on this object we have a gravitational force acting in this direction, and to raise it we have to apply at least some force that is more than this gravitational force, and only then we can get some motion in that direction. So what is this downwards force? Well, this downward force is obviously mass times acceleration again. So the mass of the object is m, and what is the acceleration of this object in this direction if we leave it? So that is g. So obviously this should be the force that is acting on this object in this direction due to gravity, m into g, mass into acceleration. Now obviously we'll have to apply some force which is at least more than mg. So what is the minimum force required to lift it? Well, if we apply something greater than mg, we get some net force in that direction and this will start accelerating. But we do not want to accelerate the ball right now, because we only wish to give it potential energy, or else I will complicate things, right, if we put in kinetic energy. So we want only potential energy to be there, so we don't want some large acceleration, and we want it to be barely more than mg. So the minimum force that we need to apply is almost mg, right, mg plus 0.00001, but we can say it's almost mg, just a bit more than that, so that we get some motion in this direction, right? So we know the potential energy should be equal to force, so force should be at least equal to mg, mass times acceleration in the downwards direction. So you have to cancel, this is the gravitational force, so we have to at least apply this much amount of force to make it move in that direction. And what is the distance that the ball travels under the application of this force? Well, we obviously, the initial position of the ball is this at the ground, and after the application of the force it reaches some height h. So the distance traveled is this much, which is clearly h. So we can simply multiply this by h, and what we get here is Pe equals mgh. And well, that is the same formula that we had arrived at in the last module, mgh, remember? So potential energy equals mgh, and this is the mathematical derivation of the formula for potential energy of an object. And we have used the equivalence, the definition of work, which is if we do some amount of work on an object, that is the amount of energy that the object gains. So using that, we have come up with this expression, and this is the same expression that we had come up. So in that one, we had just used some experiments to come up with the expression, but this is the mathematical derivation using conservation of energy. So how did we use conservation of energy? Well, we said that the work done should always be equal to the energy gained, because we cannot destroy energy. So if we are doing some work, if we are losing some energy by doing some work, that object on which the work is being done, the positive work, that should gain an equal amount of energy. And some of you had asked me the units of work. Well, the units of potential energy and kinetic energy. Well, we can see here that work equals potential energy. So because they are equal, they have to have the same units, right? Obviously you cannot have newtons here and meters there. If this is in joules work, then even potential energy must be in joules, and it makes a lot of sense, right? For example, if I have some money and I'm giving you some money, let's say I'm giving you 50 rupees, so you know that the transaction has a unit of rupees. So obviously money should also have the unit of rupees, right? If I'm giving you 50 rupees, the amount you get, it should also be in rupees. It cannot be in dollars, right? If I'm transacting in rupees, you should get rupees. And so if I'm giving you something, so work is the process by which you give energy, right? It's like the transaction, and potential energy is like the money, or kinetic energy is also like the money. So they should have the same units, and that is the derivation of potential energy.